Welcome to the second part of Unit 9. In this part, we're going to work examples regarding uniform circular motion. Our first example involves a ball being rotated on a vertical circle. You're given the mass of the ball, the radius of the circle, the speed with which it's rotating, and you want to know the tension in the string when the ball is at the top and the bottom of its path. So first off, let's all be on the same page here. What do we mean by a vertical circle? Well, here is a person with, that's their arm, and they have a ball rotating in a circle on a string like this. So it's vertically oriented. Give the ground there some. So this is a vertical circle. Contrast that with a horizontal circle, where you have the person, you can draw a front view now, where they've got the ball doing a circle parallel to the floor above their head, for example. It's not a very good drawing, but something like that. Okay. So at the top of the circle, the free body, the diagram of the ball looks like this. You have the ball's weight and you have the string both pulling downward. So in this case, F net equals mv squared over r, because we are doing the centripetal form of Newton's second law, if you will. We have two forces which cause the net force. The tension and the weight are both in the direction of the acceleration, which means the tension equals mv squared over r minus mg. Okay, well, plugging in numbers. The mass is 0.3 kilograms. Velocity was 4 meters per second. We got to square that. Divide by the radius, which was 0.5 meters, right? Yes. Subtract off 0.3 kilograms times 9.8 meters per second squared. And you get that the tension at the top is 6.7 newtons. Okay, so now let's go look at the bottom of the circle. At the bottom of the circle, we have two forces acting on the ball still, but now the tension points upward because the tension, the ball's at the bottom of the circle, which means the tension or the string has to go upward from there to the center of the circle. Acceleration is going to be pointed towards the center of the circle, so that's upward. So now if I do F net equals mv squared over r, I have the tension in the direction of the acceleration. The weight is in the other direction. That has to equal mv squared over r, or in other words, tension equals mv squared over r plus mg. Plugging in the same numbers from before, 0.3 kilograms, 4 meters per second squared, 0.5 meters, plus 0.3 kilograms times 9.8 meters per second squared. And here you get 12.5 newtons. So as the ball goes around in the circle, the tension in the string must change. It is greater when the ball is at the bottom and less when the ball is at the top, which is why when you twirl a ball, or anything for that matter, you can kind of feel it pulling differently as your hand does the circle. Next example. So why is it advantageous to bank a curve on a road? Let's start by thinking about a non-banked curve. So this is a flat road. So if I look at the front view of the car, and you guys know how great my artistic skills are now. So this is a tire, that is a tire, and that's my car. Center of the curve is this way. Okay. Now if I think about the free body diagram here, I have a normal from the road acting on the car. I have the car's weight. And then I need something pointing towards the center of the circle in order for this car to turn. The force that I have that can point that way is the friction between the road and the car. And this force pointing that direction is gained through turning the wheels of the car. Okay. So when the road is flat, the only force that I have, or that anyone has to rely on to get you around the corner, is friction, which, if it's icy out, you may not be able to turn and go around this curve. You don't have any friction to cause that. Now let's consider the banked curve. If we have a banked curve, these are particularly noticeable, say, on racetracks. So I have an incline here. I have my car. Again, tire. This is a front view of the car. The center of the curve is this way again. So I need my acceleration still pointing that way. So in this case, we want to keep our coordinate system matching our acceleration. So we don't want to tilt, even though we have when we dealt with inclines in the past. Okay. If I think about the free body diagram of this vehicle, I have a normal force that points perpendicular to the surface, so that's at an angle. I have the car's weight, and then I have friction. And friction will point along the surface of the road. It turns out the normal force and the corresponding friction force are always at 90 degrees. So since the normal force is angled, the friction has to be as well. Okay, now I'm going to redraw my incline here really quick because we got some angles we got to work with again. I'm drawing a second line, this dotted line here, that's parallel to the flat surface, the bottom, if you will, the x-axis. This angle will be theta, and now if I draw the perpendicular to that at that point, that makes this angle 90 minus theta. So this is 90 minus theta, and this is theta. Now if I think about forces, I have two triangles I need to consider. The first angle is theta, friction here. In the horizontal direction, I'll have FRC, and that will be the side adjacent, so that would be the cosine of theta. The other triangle I have has NRC. This angle is the 90 minus theta. Cosine again of 90 minus theta. 90 minus theta. I almost made my zero into a theta. That would have been bad. Okay, so now if you think about F net equals mv squared over r, I have two forces that point in the direction of the acceleration. I have the x component of the friction and the x component of the normal force. So both of those point inward, so FRC, oh, I lost my C for cosine. Let's try again. FRC cosine of theta minus NRC times the cosine of 90 minus theta has to equal mv squared over r. Now consider, if this is frictionless, that means that this term goes away. There's no friction, that's got to go away. But, oh, and this should have been a plus sign because those both point along the positive x-axis. But because the angle, or because the road is banked, I still have the normal force, which can cause my car to go around the circle. I have to do it at a very specific speed for the radius of the circular radius of the curve, but I can do it because the curve is banked. Okay. And lastly, you'll notice that this example is called Earth orbit number 1, which should make you think, if there's an Earth orbit number 1, that probably means there's going to be an Earth orbit number 2. And you are exactly correct. You will see Earth orbit number 2 in Unit 9, Part 4. So it's coming. It's just a little off. A little ways off. Okay, so for this, we're going to consider the Earth orbiting the Sun. So here is my Sun. Here is the Earth. And here it is orbiting. Okay, so caveats. First, the Earth's orbit is not perfectly circular. But for the sake of what we're doing, it is close enough to being perfectly circular for us to get the results we need. Okay? It's a good first approximation is what I'm saying. The masses here, is the Earth's mass perfectly 5.94 times 10 to the 24th kilograms? No. The same thing for the mass of the Sun, or the distance between the Earth and the Sun, right? I think the only number on here that is more or less exact is the number of seconds in a year, which is a really, really big number. Here, let me add a couple of commas. It's 31,536,000 seconds. Okay. So what force causes the Earth to orbit the Sun? That force turns out to be the gravitational force. Okay, but it's not gravitational force like W equals mg, because remember, that's only valid when you're dealing with objects near the surface of the Earth. And the Sun is certainly not near the surface of the Earth. It's 149.6 times 10 to the 9 meters away. Okay, so there's a different form of the gravitational force, which we will be learning that we will use for this. But for the moment, what really matters is the force that causes the Earth to orbit is gravity. And we can find how big that force is by knowing the parameters that go into it moving in a circle at constant speed, or approximately in a circle at approximately constant speed. Okay, so the next question is, how big is that force? So the first thing I'm going to do is I'm just going to rewrite our numbers. The distance from the Earth to the Sun we were given on the last slide is 149.6 times 10 to the 9th meters. We were told the mass of the Earth was 5.94 times 10 to the 24th kilograms. And what we know is the net force will take on the centripetal form, mv squared over the r, where this mass is the Earth's mass, because it is the one that is doing the orbiting. It's the one that's moving in a circle. To do this calculation, we need to know the speed with which the Earth orbits, which we don't have at the moment. What we do have, however, is the time, which was 31,536,000 seconds. And we know we're approximating the orbit as moving in a circle at constant speed. So if we think about this, here we have a circle. The distance around that circle is 2 pi times the radius, and it's the Earth-Sun distance, which is the radius, divided by the time. And that gives me the speed, the magnitude of the velocity which this planet is orbiting the Sun. The Earth is orbiting the Sun. So if I take 2 pi times 5.94 times, that is the mass. Let's not plug in the mass for a distance, shall we? Let's try 149.6 times 10 to the 9th meters, divided by that really big number of 31,536,000 seconds. And if you plug that all in, you get a velocity of 2.98 times 10 to the 4th meters per second. And that is a 4. And all of my 4s today are looking like 9s because this thing keeps goofing up. Okay, so reiterating, the net force is caused by the gravitational force. The mass that matters here is the Earth's mass, so 5.94 times 10 to the 24th kilograms. The speed is the number we just calculated, 2.98 times 10 to the 4th meters per second. And remember, you got to square all of that. And divided by the distance, 149.6 times 10 to the 9th meters. And if you do all of that, you get 3.53 times 10 to the 22nd newtons, which is a really, really big force. But we're dealing with planetary scale, so hopefully it's not too surprising for you. This concludes this section of this unit. In the next section, we're going to introduce the law of universal gravitation.